Thanks, guys, for joining. Welcome to the webinar, Performance Optimization Matters at the Edge. I'm an Intel Edge AI Foundations candidate as well, same as you. I'm here to talk about parallelization on Intel C++ compilers. I've completed a course on parallelism on Intel architecture, completing around 4 or 5 challenges. And I would like to talk about OpenVINO's involvement in based on like Intel C++ compilers. First of all, like I would like to talk about OpenMP. OpenMP is Open Multi-Processing OpenMP API, which helps in multi-processing and multi-threading applications, and also for creating vectorized code for compilers. So OpenMP comes as a feature for every compiler. I know 3 compilers which has like OpenMP feature. One is the GNU C++ compiler, Intel C++ compiler, and CLang compiler. The CLang compiler is mainly it's been used for converting JavaScript code to C++. There are implementations of CLang compilers such as like mscript and JS, which actually executes the code in native language, and you get the performance similar to C++ code executing in native language. So the exercise that I would deal with here are based on pragma directives. There are a couple of other pragma directives which optimize the code and optimize the compiler, does the vectorization process, and improves the performance by 8 or probably 16 times. There are different libraries for doing that. OpenMP is one of them. So main common pragma directives are parallel with num threads 64, that assigns OMP threads as 64 and executes the block of code in parallel. The second one is a OMP for. It's attached with the for loop, and the for loop is called based on a scheduled call. The for loop is divided into chunks, and each chunk is called as a function. OMP parallel for executes the chunks in parallel, so it schedules the call as well as it executes in parallel with the specified number of threads. SIMD is another vectorization process by which you can vectorize the code into different chunks and execute either floating point operations all at once. So SIMD is basically single instruction, multiple data. A single instruction is sent to multiple vector units, and they executed in parallel. So that is as well a parallelization process. SIMD process is been shown here. So it's related to making a stride within for loops. So if you have multiple for loops, you create multiple strides, and they are closer to each other, so that you access the memory locations closer to each other, and that's faster, because if you access 0 and probably 18 at the end, that is not performance wise. That's the sort of like vectorization which SIMD can do. So this is one of the examples which parallel num threads execute. In this example, there's a for loop inside the parallel num threads block of code. So the entire for loop is run inside, is allocated around 64 threads. And within the for loop itself, you can customize the code. Like, for example, you can add the other OMP4 parameters, which can schedule the code. Sorry, that's a battery. So this is an example of OMP4 where the calls are scheduled. This is a typical example of a Fibonacci series. It takes the sum of previous two integer values. OMP parallel for executes the code in parallel. Here there's a bit of a trick, because when you compare parallel for and SIMD code, in the SIMD code the variable A is very different. I mean, it's a different variable than sum. It may be a copy or it may be a different variable as such. In this vectorization loop, the sum is not aware of what A does, so it can vectorize and parallelize easily, in the sense like it doesn't have to calculate the preceding or succeeding values in order to conduct the parallelization process. So for memory access locations, it's quite flexible with it. It's called, the term is called memory aliasing. So in this case, there is memory aliasing, and vectorization doesn't work out well because it may throw up errors. In this case, there is aliasing. In this case, there is no aliasing. In this case, there is aliasing, which is good for vectorization. No, not aliasing. In this case, there's no aliasing. It's a different vector itself. This one is aliased because sum I plus 1 is alias of sum I. So we have covered for loops and parallel for loops. Now I'll talk about the single block of code, where only a single thread is allocated for that inner block of code. Here the inner block of code is the for loop, and the no wait flag after the single term denotes asynchronous process. It doesn't wait for the for loop to finish execution. There is an extra line of code you can add after the single no wait, which is task wait, which will wait for all the process which has called no wait before, or which is executing in an asynchronous manner, and it will wait there, and then all the tasks will be completed, and further process will be having all the data synchronized. Barrier is another type of synchronization process, where not only tasks but multiple processes as well as threads can be included within the barrier loop, because it's a global task wait basically. Atomic and critical are used for calculation purposes mostly. So you write atomic write is you write to a variable line by line. Critical means the section itself is critical and it will stop execution and then execute that particular line. Atomic can execute that particular line without breaking any other regions. So these are similar to semaphores or mutexes you normally see in C# or C++ or Java. A parallel is a block where the code within the section is ensured to be executed even though no wait is present completely. So within the section, all of the code is executed, is ensured to be executed, even though no wait is present inside the code. So when it finishes execution of the block, it will be executed completely. It will be synchronized. Parallel sections are subsections of the parallel block. If you create 2 or 3 sections, you can create manually like 2 or 3 sections and enclose that sections into parallel sections. So each of the section will be a parallel loop, parallel block. This is the example I spoke about earlier. Parallel, a single no wait inside a parallel. So the inside the loop, the block inside single no wait is executed without waiting, and block outside the no wait is executed after every thread joins. I have certain set of problems that I can go through. This is a popular function. It's a kind of a methodology used. It's called stencil. Intel uses there's another stencil library called yet another stencil library, YASL or YASK. Stencil are main key operations which gets analyzed in bottlenecks as well. Stencil can be a convolution operation you see in computer vision, or it could be a gradient operation you see in computing gradient. Apart from gradients and computer like convolution, stencils are like possibly matrix level. Stencils are operations which operate at the matrix level. So here in this code, it's definitely like a templated code. So you can pass in any type of data into the stencil data. It could be a float, can be a float. So image class is probably a float class. There's an image out parameter here. There's an image in parameter coming from the image class. Each is a pixel data. It's got width and height selected. So there's in image, out image. These auto vectorized for loops for compilers. They will be executed. And the gradient is computed by computing all of the neighboring regions. You can see the middle term here. If the computed value is less than 0, it assigns a black. If it is greater than 255, it assigns a white. And you get horizontal and vertical gradient, in a sense, like a Sobel one. So it's about optimizing. We know the code works well. That works well everywhere, like in whatever language you use. But for large operations, if you have large image and large matrix, it's better to always vectorize the inner for loop So the code for SIMD should go here. Once you vectorize SIMD, you can add the parallel here. So you can parallelly run the SIMD process together. That's very efficient. So the multi-threaded solutions provided here are OMP parallel for with SIMD vectorized inside. This is the strided format that they use in normal image format. Like if you have rows here and columns here, it's I into the columns plus J. Does the indexing. So the compiler can easily pick up what the parameters are, what the parameters are, and it can automate the parameters. So we'll go through the SIMD example. SIMD example is just vectorizes SIMD and then it follows the auto vectorization format for the outer for loop. So there's quite a few examples, like it uses memkind library, it uses MCD RAM, which is larger bandwidth memory. SIMD, the compute gradient code has been explained here. SIMD is a convolution process. Like you can think of stencil. Sorry, stencil is a convolution operation which scales over. I mean, which moves over the entire image rows by columns and produces an output image. Now, model optimizer has several components. One is a graph component. It builds the graph. The graph library builds the graph for the model optimizer, and it can parse each of the deep learning model from the implementation of the deep learning framework, which makes the graph easier to search within the framework itself. There's OpenCV and OpenVX integration with OpenVINO. OpenVX is a graph API written for video processing, and it's a graph API which does computer vision. OpenCV is a library written in C++. Then we've got another technology which is OpenCL, developed by Apple. It's mainly written for GPUs. And you can customize the hardware level to include CPU, FPG, and VPU. There's a Python version of OpenCL available, which is PyOpenCL. You can set up all the context layer inside the Python code, and you can execute only the C code inside the Python execution context. So it compiles on the fly the C code and runs the C code inside the Python package. I have a demonstration for that. So this is OpenCL Python library, which I ran in my local. I don't have a GPU local, so I installed OCL Grind, which is a simulator for OpenCL. So you can run OpenCL code inside any like Intel HD graphics or CPU. So this is the C code that it runs inside the program context. The model optimizer has an internal graph library which does the work of building the graph. You can search through the graph for different layers. Now, inference engine is what I'm talking about because it's got many C++ layers. Inference engine API and inference engine framework written in C++ has many parallel processing done. Inference engine process the IR model and weights and biases are supplied to the inference engine by the model optimizer from the pre-trained model. As you guys know, you might have seen the code of inference engine in OpenVINO as well. They use Intel TBB framework, which can maintain high complex code compared to OpenMP. It uses POSIX threads, Intel MKL as well. Now, TBB and OpenMP are different in the sense that one is mainly focused on repeated for loops, and TBB can create functions. OpenMP is mainly based on array-like definitions. So, like if you use vector definitions or arrays, OpenMP can vectorize and parallelize them easily. But TBB, on the other hand, you have to call a different function in order to execute the function in repeated for loops. With OpenMP, with just 2 or 3 lines of code, you can improve the performance by 3 or 4 times. I tried the security barrier demo and I added few lines for OpenMP. I added some parallel sections. I cut, copied, paste some code, and then made an envelope of the code into a section, and got improved by like 3 times. As I said earlier, the code complexity can be dealt by Intel TBB. It's been built The foundations is like the Intel TPB for parallelization. But OpenMP, on the other hand, can perform vectorization, can perform complex calculations like reduction on arithmetic operations. Now I have some other examples which I can demonstrate here as well. This is an example written in P threads, POSIX threads. This sort of a definition is common because you can define the number of threads in a struct. The main function you call is pthread create, and each of the thread has will be created using pthread t. You create the thread and then you join the thread and you wait for the thread basically. So you exit the thread and task is done. Now multi-threading using C language here, using Intel C++. You can write complex codes which connects each individual task, each individual task into another ones. Like you can specify the you can specify the single loop inside, single thread inside the parallel loop with no wait, and then you can keep a task inside the single. You can encode what is the order of the task execution, like you can group the tasks and then you can connect them together. So what this does is, this checks for the final state. So when this parameter is the index parameter, the length parameter, and when the index equals to the final item, it stops the execution. And there is a dependency flag as well, dependency task, the task dependent parameters, which are inputs and outputs. So you have to define the output and you have to define the input. The output is generally defined from 0 to 1, 0 to R, or 0 to the particular length that you use. And the input is defined as the next segment. That's one type of threading you can actually use. So SIMD, as I had explained before, it's single instruction, multiple data, which executes the vectorized code in multiple processing units. SIMD is a different type of processor. People have written large fast Fourier transforms in multiple radix n algorithms. They have achieved the highest performance there. On the right hand side is the OpenCL context, similar to the OpenCL. Is basically the OpenCL context. At the bottom, the kernels are created inside the kernel execution context inside the GPUs, and each process is bound with the kernels. So OpenCL executes based on if the arithmetic operations execute based on SIMD process, the OpenCL, if the vectorization is done based on SIMD process, the OpenCL code or the GPU, mostly the GPU, majority of the GPU code is following SPMD method, single program multiple data, which means the program data is sent to each execution unit, and then the program itself is executed together. That is more efficient because, as you can see here, there's a image convolution program which is compared between OpenCL, OpenMP, and normal sequential process. And OpenMP is found to be finishing in 0.05 seconds, and OpenCL in 0.96 seconds, close to 1 second. This is because OpenCL takes time in creating these kernel settings for the GPU. GPU has to allocate memory for each execution unit. GPU's floating point is different from floating point ranges, and everything is different from the CPU ones. So this is the convolutional neural network, which was run between OpenCL and OpenMP. It generates more data than, as you know, like it generates more data than the input. And also it generates out of range data as well. If you provide unsigned byte, it will definitely like go on to the floating point numbers. So this is an example of OpenCL code. First, you have to query for the platform. You create the context, create the command queue, create the buffer content for code to execute here for the variable, like basically similar to the C types program you see in compatibility between Python and C++. You have to create a C types variable or the OpenCL buffer here initially, and the context program is sent inside. Then you can compute inside either OpenMP or do any sort of like program or parallelization program. OpenCL is definitely different. In GPUs, it's different. So it sums here and calls the function individually. This is another demonstration of the Intel's example. The main C file, it's a SIMD project. So they have optimized and obtained good stats on computing an integral. So the integral itself has an accuracy version. It, if you send the range of values B and A, it computes the error to norm ratio. So error to norm ratio, the accuracy definitely, yeah, it's it computes the proximal values, I think. So in code itself, it's in n number of trials. For every trial increase, it passes in the initial range, first range and second range, computes the accuracy here, and provides us the performance values. So our main function is the compute integral function, which is provided in worker.cc file. So in the compute integral function, there's a special function called, there's a special pragma definition called SIMD reduction, not just the SIMD reduction with a plus sign. A plus sign indicates its operation is plus. So if you are summing everything, if this is minus, this will be minus here. So what it does is it computes individually, it breaks it apart into different pieces. It computes individually the sums, and based on a tree structure, it keeps on iterating and finally reaches to a single sum. So let's try executing the function. I've changed the make file to G++ to be compatible with this website. OpenMP does accept the OpenMP library. So when I run make all, it creates an integral. I can run the integral using run. The make has generated the integral function. So let's check what the integral values are in the main C file. It's 1000 into 100. It used to be 1000 into 1000 into 1000, which takes time to load. So I've reduced to, I'll make it 1000 into 1000. And again. And if I run integral, for the nth trial, for the 10th trial, I get this time. And if I run the reduction one, so what reduction does is, actually I'll execute and see the output. I think this is higher. This is 1000, 1000, 1000. We used only 2000 before. This should show us a better 73.8, 74.4. Okay, so they've used atomic here, which means the accuracy has been higher for lower calls, I think. Okay, it's based on the striding values. Yeah, okay. So N, since this is schedules, normally you can see for N equal to 9, this is lower, this is higher. For N equal to 5, this is the parallel program, the scheduled one. For N equal to 5 is lower. For N equal to 5, it's higher time. So it's based on the schedule. You can actually schedule it to 4 or 5. Default is a 4 option. And that's why the SIMD reduction is not effective for 10, but it is for 5 and 9. Here they use atomic for improving the accuracy. So each time it doesn't get overwritten when you run parallel process. Let's take another example as well. Okay, this does parallel for and SIMD reduction. Yeah, because of this striding, it doesn't do the tiling option. Tiling makes the process more easier to vectorize the for loop, and since it doesn't use the striding option, strider access as shown before, it is not effective to have the single for loop here. Not this one. So do you guys have any questions at the moment? Okay, then thanks for coming in. Thanks for being attentive on the topic. Try some examples and try improving your code using OpenMP. Thanks for joining. Thanks for coming in. Yeah, C++ is quite easier than the C version. C++ from Udacity's course, John A. Strostrup, he himself takes a course in C++. That's the best introductory course in C++. It explains about iterators, arrays, and templated ones. Yeah, that's the best course. I think C is harder. C is like for building computer languages and those sort of like things. Yeah, I'm happy that you guys are interested to know about C++. All right, thanks a lot for coming in. Thank you.